Okay, we're going to start section 2.3, which is norms. We've talked about norms already in the context of inner products, so let's review that. So remember what an inner product is. So we have a vector space V, and an inner product is a map which takes VW. You can plug in two vectors and get a real number, and it satisfies three conditions: bilinear, symmetric, and positive. And I'm not going to write all these down again, but I'll remind you that symmetric means this, and positive means this. And it also means equal to 0 only if the vector is equal to 0. Okay, and given an inner product, associated to that is a norm, which is to say the norm of a vector v is the inner product of v with itself to the 1/2, the square root of that. And what we're going to talk about today is the theory of norms independent of inner products. So pretend you didn't have an inner product, and you just look at this operation which takes a vector, a single vector, to a number. And this operation has certain properties, and we're going to say what those are and talk about norm. Those things are called norms. Okay, but for now, let's not talk about the sort of general theory of a norm. Let's just say, suppose, here I'll put it as a question. Suppose you have an inner product, and using that you define a norm. The question is, what are the properties that that the norm has? So what do I mean by that, properties? What I mean is the following. The norm, it's a function which takes the vector space to the real numbers. And what that means is you take a vector and you go to its norm, which is a real number. And what kind of properties does this function have? So what are the properties of this map? So the properties of this we just talked about. There's bilinearity, symmetry, and positivity. So, well, let's take the last one first. It's clear that one of the properties that the norm map has is that the norm of any vector is greater than or equal to 0, and the norm of the vector is equal to 0 if and only if the vector itself is equal to 0. So that's just like the positivity condition for a bilinear form for an inner product. So that's the positivity. That converts directly to this positivity condition. And what about bilinearity? Well, we only have one argument here. And if you think about it, one of the things that's easy, one of the easy properties, is that the norm of C times a vector is equal to the absolute value of C times the norm of a vector. This property is called homogeneity. And let's see why that's true. What's the norm of C times V? Well, it's the inner, by definition, it's the inner product of this vector with itself. And by bilinearity, you can pull this first C out, and you can pull the second C out, and together they give you a C squared out front. V. The square of this is this thing. And so when you take the square root, you got to be a little bit careful here. You get the square root of C squared V, which is to say the square root of C squared times the square root of V. And this is the norm of V. And what's the square root of C squared? Well, everybody that said C has to stay after class and clean the erasers. It's absolute value of C times the norm of V. And why is it the absolute value? Well, because it's the square root of a positive number. It has to be positive. If you wrote C, that might be negative, and that's not allowed, so that's why you get the absolute value. And then the last one is, well, the last one is one that we've already seen, and it's just the triangle inequality. Oops, less than or equal to the length of V plus the length of W. So that's the triangle inequality. So these are, if you have an inner product and associated to that is a norm, the norm of that coming from that inner product, it satisfies these three conditions: positivity, homogeneity, and the triangle inequality. Well, I hope everybody sees what's coming next. That's a definition of a norm. So here's a definition. And what this is a definition of is a norm on a vector space. And it's all of the things that I just said about the norm coming from an inner product, but without the inner product. So it's a map written like this from V to R, satisfying those three conditions. The first one was positivity. The second one was homogeneity. And the last one is the triangle inequality. And so the question is, well, so now we're going to talk a little bit about norms. And an obvious question is the following. Does every norm come from an inner product? So we saw one way to find norms, which is to make an inner product and then take the associated norm. But is it possible to cook up a norm that doesn't have anything to do with an inner product? So before I start talking about that, let me make a key observation. And it's the following. So we talked about if you have an inner product, you can make a norm, which is to say you take the norm of V to be the inner product, to be the inner product of V with itself, square root. The question is, what about going the other way? Suppose I gave you a norm and I told you it came from an inner product. If I gave you the inner product, you'd tell me the norm, but if I only tell you the norm, can you tell me the inner product? And the answer is yes. And it's from the following simple observation. Look at V plus W, inner product V plus W, minus VV minus WW. What's that equal to? Well, we can write this out. It has 4 terms, 2 from here, 2 from here. You get VV plus the cross terms are VW and WV, and by symmetry that's 2 VW. And then the W term is plus WW. And then you're subtracting off the VV and subtracting off the WW. So this goes away and this goes away. And what you wind up with is 2 VW. And so the conclusion is what? Well, on here we have the inner product of V and W, and on the other side we have everything over here is a norm. This is the norm of V plus W squared, and this is the norm of V squared, and that's the norm of W squared. So this is what's sometimes called the polarization identity. Which says that you can compute the inner product of 2 vectors if you know how to take norms. All right, so again, let me say what the significance of this formula is. It's that you can compute the inner product in terms of the norms. And so what that says is if I give you a norm and you think it comes from an inner product, well, there's only one possible inner product it could come from. And the inner product would be defined this way. Okay, so let's look at a couple of examples. So let's start with some examples on the usual Rn. So at the moment, well, there's, if you take the ordinary dot product and you take the associated norm, you get that the norm of V is summation of its coordinates xi squared to the 1/2, where V is x1 xn, right? Because the summation of the xi squareds is V dot V, so that's what you get. And of course, if you take any inner product, you get a formula like this. But rather than looking at those, I want to look at some other kinds. So here's an example. You can define the norm of V to be just the sum of the absolute value of the coordinates. Is that a norm? Well, let's see. It's positive. And it's homogeneous. If you put a scalar in here, you get a scalar in each of these, and it pulls out as the absolute value of the scalar. So the homogeneous is easy. And the triangle inequality is also clear from this formula. So this is an example of a norm. And so here's a first example of a norm which doesn't obviously come from an inner product. And as a matter of fact, we'll see in a minute that it doesn't. Another example is you can take the norm of V to be, this is kind of an interesting one. You take the maximum of the absolute value of its coordinates. And I suggest you stop the video here for a minute and verify these three properties for this particular norm. Okay, so, well, I'm not going to do that. I'm assuming that you did. This norm is called the 1 norm. This norm is called the infinity norm, and this norm is called the 2 norm. And they're all special cases of the p norm, which is you define the norm of the vector sub p is you add up the absolute value of each xi and raise it to the p, and then take the pth root of both sides. And this makes perfectly good sense for any real number p greater than or equal to 1. So, for example, when p is equal to 1, you get summation absolute value of xi to the 1, and that's this norm right here. P is equal to 1. And if you take p is equal to infinity, well, let me do p is equal to 2 first. If you take p is equal to 2 first, if you take p is equal to 2, that's this one right here. And you don't need the absolute value there because the square of any real number is positive. And if p is equal to infinity, well, if you think about limits for a minute, if there was just one term here, it would be x to the p to the 1 over p. That would just be x. There's not just one term, there's a bunch of terms, but the biggest term dominates. And so in the sense of a limit, all of the other terms are irrelevant, and when p is equal to infinity, you're getting this one right here. So you can just take that as the definition when p is equal to infinity, and it really makes sense in some limiting. It can be made precise. And, well, a key fact is that only p equals 2 comes from an inner product. So I'm not going to prove that or talk about that too much, but I might talk about that a little in class. It's a basic fact that only one of these comes from an inner product. All of the others are norms, but there's no associated inner product. Now, notice that one thing that that means is that, for example, if you took v infinity, you could always, the only way to that would be related to an inner product would be if the inner product was the inner product of v plus w infinity minus the inner product of v infinity minus the inner product of w infinity, 1/2. I'll just put the 2 here. And, sorry, and I also forgot the squares. And so this is the maximum value of the sum, the maximum entry of the sum. And this is the maximum from v and the maximum from w. And if you just look at that for 2 seconds, you'll realize this is a perfectly well-defined function, but it's certainly not this thing right here. This function that we define this way is certainly not bilinear. So that's the basic idea when p is not equal to 2. And this definition has a key generalization to, this is the vector space of continuous functions on an interval. Let's say the interval 0, 1. You define the p norm of a function is you integrate the absolute value of f of x to the p, and you take the whole thing to the 1 over p. So this is like an infinite or continuous version of the previous one. You think of an integral as being like a sum, and it's just some sort of continuous sum. And so this is the analog of the p norm that I defined a minute ago for Rn. And I'll let you check that these are all norms on V for any p bigger than or equal to 1. Oops. Well, I think that's a good place to stop. There's a couple of other things in this chapter which I'll mention very briefly in class. I'll just say what they are now, and you might want to read about them in the book. There's a very simple concept of unit vector, which is if you have a norm on a vector space and any vector v which is not equal to 0, you can take the vector v over the norm of v. And this is a scalar, so you're multiplying the vector by this scalar. Then the length of this vector, or I should say the norm of this vector, is equal to 1. So that's called a unit vector, and this tells you how to find a unit vector. And so, whoops, that's interesting. And that's easy, and hard, or not so easy, is the notion of equivalence of norms. And I'm not going to say anything about that here, but there's a section in the book about it, and I'll mention it briefly in class. See you tomorrow.